Okay, so hello everyone. Thank you for coming to the 3501 Crash Course for Water Resources in Term 1. I'm Akshara, and my other co-tutor Janice is not here today, but she sends her regards. Yeah, we're just going to teach you a little bit about water resources and also groundwater resources. So groundwater resources is from weeks 7 to 10 or weeks 8 to 10, and that's the part of the course I will be teaching. And the hydrology part is the section that Janice will be teaching. So I guess without further ado, I'm going to start Janice's section of the course.
In the time we have, and maybe some key topics here and all right, good evening, everyone. I'm so sorry I couldn't make it today, tomorrow, but I'm just going to be filming this in advance, so at least you guys will have something to watch as Akshara goes through the later parts of the water resources course. So please note, I won't be covering everything today, just some topics that are easy to cover in the time we have, and maybe some key topics here and there. This is a crash course, so just treat it like an introduction for what's to come, and hopefully you guys will have gained something useful out of this small session. So week one of of water resources, we'll be covering evaporation, rainfall, stream flow. I'd go through a few of these topics. Week two, flood frequency analysis. Week three, we've got design rainfall as well as the regional flood frequency estimation. Week four, we're only going to be covering lightly on the first half of it, which is catchment and delineation. Losses, rainfall runoff modeling, that is a bit more complex and there's a lot more notes on that. So unfortunately, I will not be touching on that for this session. I believe Akshara will be covering with you guys week 7, weeks 8 to 10. She can correct me in person if that is not true, but yeah, let's get started. So, week one, we've got the hydraulic cycle. So there's a concept known as the water balance. And the water balance is just a conceptual model that describes storage and movement of water on Earth. So when we mention storages, we're talking about things like reservoirs, lakes, rivers, dams, groundwater, aquifers, snow caps, glaciers, all that is natural and man-made, both in consideration. It's just whatever stores bodies of water, however little it may be or however big it may be, from oceans to glaciers, right? And then there's the movement of water on Earth to consider. It's in two parts. There's storage and there's the movement. Movement of water between these systems, you're talking about evaporation, sublimation, runoff, condensation, precipitation, transpiration, etc. So the list goes on and on and on. So you can almost think of it kind of, it's not like, comparing pears and apples, but it's quite similar. You can think of conservation of energy. Water is very similar. The amount of water stays the same within the system. The form just changes or it moves around, yeah? Similar with energy, how you have gravitational potential energy transforming into kinetic energy. You also have water. It melts, it freezes, it moves around in Earth. It stays the same. So, then you have two concepts here. You've got the transpiration and evapotranspiration. Both are movements of water. Whereas transpiration, it's more focused on the loss of water stored in plants into the environment. So it depends on the type of plant. It depends on if it's tree or grass, cactus, how big the root zone is, what kind of plant it is, variables like humidity, temperature, carbon dioxide, wind speed also matters. It's just about how plants would absorb the moisture or water from the atmosphere, from the soil, and store it in their roots, in their leaves, in the systems. I'm not too big on plants. I don't really know how plants work, but that's the idea. It's the idea of water being moved by plants through their root systems, so on and so forth. Evapotranspiration, and that's the most common kind of movement of water that you're going to see on the surface of the Earth, is a combination of both evaporation and transpiration. And let's go to the next slide. Should be here. Yeah. So you've got the Dalton's law, which describes the rate of evaporation, millimeters per day, and it is a function where it's proportional. It's the difference between the saturation vapor pressure minus the actual vapor pressure to proportional to a certain constant. So you might want to ask, well, what is the vapor pressure? So vapor pressure, EA in this case, is the pressure of a vapor in equilibrium with its liquid and solid phases. For example, it's when conditions are such that the substance can exist in both liquid, solid, or all three state phases of the materiality. So you're looking for a certain kind of substance. Well, you're basically asking what is the tendency of its molecules to escape from its liquid or from its solid form. And that comes in two forms, right? You've got condensation as well as evaporation. That's the two ways molecules can escape or join in when you have like a body of water or like ice or like a solid, right? Condensation, in that case, it is, well, if more molecules are arriving than molecules are leaving, there is net condensation. On the other hand, if more molecules are leaving than arriving, you have net evaporation. So that's what vapor pressure is. That's the actual vapor pressure. That's what EA is. On the other hand, saturated vapor pressure, ES, that is when the vapor pressure, that is when, in that situation, it's when molecules are evaporating is equivalent to the molecules condensing. You're in an equilibrium between evaporation and condensation. At any given temperature, and you can see this formula right at the bottom here, ES equals to 0.6108 times the exponential of that function of temperature, right? And yeah, ES, it's the equivalent is when they're in equilibrium at any given temperature. There is a maximum amount of water that can be held in the atmosphere. There will become a certain point where more water cannot evaporate into the atmosphere because it's already full, it's already reached maximum humidity. Then there's the relative humidity, the dew point, all that concepts we're not going to cover for this session, but you will come across it in your first week of water resources. But that's the idea. There will become a certain point where you cannot force any more water to evaporate into the atmosphere without condensation happening to balance it out, because it's reached that maximum threshold for the amount of humidity the atmosphere can carry. So there are many ways to actually calculate evapotranspiration, and there's actually like three types in total. There's so on this slide you've got potential evaporation, evapotranspiration, and the one you'll become most familiar with is the Penman-Monteith. It's a series of equations. It's very commonly used for calculating evaporation, and it's because, yeah, it's just the recommended approach in the industry as well, but it also requires a lot of data, a lot of variables to be used, and you can see it there with the Penman open water body evaporation formula. So potential evaporation, evapotranspiration, that's ET0. It is the maximum amount of water that can be evaporated or transpired irrespective of the amount of water available. Say, for example, yeah, if we had an infinite amount of water based on the temperature, the humidity, all the circumstances, etc., what is the maximum amount of water we can evaporate in those conditions? Like, if we had an infinite, not, sorry, I'm mixing it up. Yeah, it's just that, wait. Yeah, it's kind of confusing when there's multiple terms, but for potential evaporation, evapotranspiration, it's just that if we had an infinite amount of water available, how much of that water can we actually evaporate with the full force of the sun or whatever temperature there is? On the other hand, you have another concept known as actual evaporation or evapotranspiration, and that's known as the variable ETA, and that is the actual amount of water that is evaporated into the air. If you had 1 liter of water in a bucket outside, no matter how hot the temperature gets, you cannot evaporate any more than 1 liter of water. There is only 1 liter of water in the bucket to evaporate. You cannot evaporate any more than that. And that's the difference between actual evaporation, evapotranspiration, and then the potential evaporation and evapotranspiration. Potential evaporation, evapotranspiration, you have as much water, infinite water. It's a theoretical example. Whereas actual evaporation, evapotranspiration, that's more about, well, what do we actually have in that bucket of water? What do we actually have in that pond or in that ocean? How much is actually physically feasible to evaporate in that situation? And then there's a third one as well. That's the Penman-Monteith evapotranspiration reference crop. So yeah, that's known as the ETRC. And that is basically looking at the rate of evapotranspiration from an idealized grass crop. It's the ideal situation. Yes, so you can see as well at the bottom here, you're saying in a hypothetical situation, if that area was covered in a grass crop, a plant, with an assumed height of 0.12 meters and a fixed canopy resistance of 70 sm, and then you also have an albedo of 0.23, and albedo is just referring to how much light an object reflects off its surface. In that very idealized situation where you have like the idealized plant coverage, the idealized crop and all of that, well, what is the evapotranspiration rate? And that's just there to like standardize and kind of there to compare like situations, right? But that's also the formula. I believe yeah, there's a lot of overlap in variables. I'm not gonna go through all of them. There's quite a lot, but yeah, quite a few of these they will be given. There's also a booklet that they'll give you at the very beginning of the course. It's very helpful. It's like the lecture notes, and inside that lecture notes, there's a lot of graphs, a lot of tables that talk about like, well, if it's this soil or if it's this plant or if it's like this height, what are the variables in each situation? It's like the standards basically, like what would you assume for this value in this circumstance? And it's very helpful. Like definitely that's what you're going to refer to when you're doing your questions later down the line, but that's where you would find all the information regarding these variables. All right. So, yep, that's the Penman-Monteith collection there. Of course, there's going to be there's a few more topics such as I believe it was radiation, looking at energy as well, looking at how this you have like black body radiation, all that, but that's like a whole nother thing to cover later down the line when you actually do the course. We can move on now to, well, week two concepts, right? Oh yeah, before I forget as well, just going back to the first lecture, the first lecture comes in two parts. You have evapotranspiration on one side of the coin, and on the other side of the coin, you have precipitation in the second half of the week. You can look at that when you start the course. But moving on to week two with flood frequency analysis, this is all about estimating floods, right? You're estimating, well, how severe a flood will be. And this is, of course, very important information to have, especially when you're trying to build infrastructure or you're trying to plan for towns in areas that may flood often, flood frequently. You want to know, well, how frequently is it? How severe will it be? And yeah, how can we actually like think of ways to build for those circumstances? It's actually very important to learn, or well, in the industry as well, just like knowing how to estimate floods and how to design for flooding, right? And in order to do that, you really need to know, well, how can we analyze floods? How can we classify floods, right? And in this case, these are the two acronyms that are quite essential in this course to know. There's the AEP and the ARI. AEP, that's referring to the annual exceedance probability. It's the probability of a flood exceeding a certain given flood level or flood height in a year. So say, for example, if I said, okay, I don't actually have the actual stats, right? But if I said there's a certain town out there that a certain flood height of maybe 1 meter, so in this town it's always gonna, like, you know, there are floods that are 1 meter in height or something like that, so everything below that 1 meter is gonna get submerged. Well then, if I said that there was a flood like that and I said the AEP of that flood is 0.01, then you can understand that there is a 1% probability each year that there will be a flood to exceed that certain height. Yeah? It's just 1% probability, 0.01, so you can think of it as, well, you have, well, let me get my pen out. You can have 1, that's just equal to 100%, right? If I had a flood that has an AEP of 1, well then it's 100% guaranteed every year there's always going to be a flood like that, right? Maybe, and then, maybe that's less of what we know as a conventional flood. Maybe that's like a, light sun shower, and that's going to always happen every single year, no matter what, right? Then on the other opposite of the spectrum, as I mentioned before, 0.01, that is 1%. And then I'm sure you guys can then interpolate, well, what is the range, right, between the two? Just like that. Then, on the other hand, you've got ARI. That is average reoccurrence interval. That is the average value of a period between exceedances of a given discharge. Yeah? So that just means, well, between a flood where it's going to flood and reach 1 meter in flood height, and another one where it's going to do exactly the same, or even more, it's going to be worse than a 1 meter flood, what is the average time in between the first event happening and then a worse or exactly same event happening again? Like, how long? Is it going to be a year? Is it going to be 100 years? Is it going to be 10 months, right? What is the AEP? So if I said, if a storm has, if a storm has a AEP of 0.0, and here's the thing, right? The two are related. AEP and ARI is related. Before we move on, let's make that clear. So AEP is basically just the inverse of ARI. Excuse my messy writing. I should have probably typed that up, but yeah, AEP is equal to 1 over ARI. So if I said I had a storm, if I said a storm has an AEP of 0.01, the storm is then going to, on average, occur once every 100 years. And that is the ARI. That's the average reoccurrence interval. I can expect that, the storm has happened 100 years later, I'd start getting worried because maybe, that storm's on the horizon now again, right? And yeah, that's basically what it is. Binomial probability, that's the whole thing that flood analysis is rooted in. It's either no flood or there is a flood. Binomial probability is either yes or no. Is there a flood or is there no floods? So, so before we stop there, for flood frequency analysis, this whole thing, flood prediction, is very rooted in probability. And it gets quite complex because of how many variables a flood can have. It depends on location, flow rates, right? We're talking about how fast the runoff or the streams will flow after a flood event. There's so much to do with terrain, to do with temperature, weather at the time, to do with like climate change is a huge factor these days as well. And they're trying to update models to reflect that. But because of there's so much to do with variables and probability, for this course in particular, they use this software called Flike, and that is Flike, which I will not go over because there's just so much details and settings to go through. It's like a whole lesson on its own. But essentially, it's like a software, and you'll be able to access it through, I believe, Citrix later down the line. And essentially, all you do is you feed it like Excel spreadsheet data. You feed it all the stream flow data, like just how fast water is running through streams, rivers, bodies of water during a flood event. Because of course, when it starts raining, when it starts flooding, the flow rates in rivers and streams and all of that, it's going to go up with the storm, and it's going to change over time as well. But yeah, you feed the program stream flow data, and then it will generate a curve that will predict the peak flow rates of a flood depending on its AEP. And you have like a variety of different probability models to be choosing from. And there's of course pros and cons to be considered. Like some probability models favor more severe flooding data, whereas other probability model favors or is more weighted towards reoccurrences. Yeah. So of course, different situation will call for different models to be used, and I believe that's like log Pearson, type 3, all of that. But yeah, that's not for today. That's not for today to cover. But yeah, definitely look into it if you have your own spare time. It's actually quite interesting, especially if you want to go into like water engineering later down the line. But yeah, moving on. Now you've got design rainfalls as well as regional flood frequency estimation. And the FLIKE models that I was talking about before in the previous slides, and ARI, all of that kind of stuff, that relies on stream flow data. It relies on someone going down to a stream with like a measuring device and then putting it into the water and, well, seeing how fast the water is going, what's the velocity. And sometimes in more rural areas, or maybe where the conditions are more dangerous, you won't have stream flow data. How else can you actually estimate floods then? So what you can do is you can still use information from nearby sites and use rainfall to then interpolate stream flow. And there are two very common methods to approach this, and these are the two methods that the course will address. Number one is IFD curves. Second one we'll cover later, but yeah, IFD curves first. These are known as design storms. And essentially, IFD, that's intensity, frequency, and duration. And all of this data is collated by the Australian Bureau of Meteorology, BOM. It limits the variables to these three to create a model of a storm that would be expected based on the AEP you feed it, as well as based on the location. So I've included a little screenshot of what it would look like. So you go onto their sites, there's a whole site for like IFD curves, and you just insert information. You insert, well, I don't know if you can see there, but there's requested coordinate. You'll enter latitude, longitude, and then it'll tell you, well, this is the nearest grid cell on their grid, on the database, which is slightly off, but it's close enough. That's the whole point of it, is some areas you won't have streamflow data, so you just gather from nearby sources. And then looking at the table, you can then see there's a legend, 1%, 2%, 5%, 10%, so on and so forth. That's talking about the AEP, right? The probability, the annual exceedance probability, how likely is this storm to occur in a year. So of course, 1% storms, those are more rare, those are more severe. And you can see on the left, there's the rainfall depth. So that's how deep the rainfall is going to get, and that's over duration, and that's on a exponential scale. You've got minutes, hours, and days. So the longer the storm is lasting, of course, well, the depth is going to be deeper. There's going to be more rainfall happening and all of that. And then, of course, more frequent storms, 63.2%. That's going to be a less severe storm. And you can see correlation there. The depth is a lot more shallower. Yeah, but of course, it still escalates as time goes on. That's the whole thing. You use these graphs, you have the AEP, you have the location. From there, you can then look at models, design storms, and kind of estimate, well, if this storm were to happen at this place next year or something, this is the depth we're looking at. And then maybe that can then inform your infrastructure. Do you elevate certain housing? Do you have drainage to accommodate for these kind of rainfall amounts? So on and so forth. Now, the second method that you can use in order to estimate, well, flooding and all of that is RFFE, and that's the Regional Flood Frequency Estimation, and that is a model that is made by ARR, which is like, I think it's like an institute or an organization. It's the Australian Rainfall and Runoff. But yeah, once again, this one's fully accessible online, both the IFDs as well as RFFE. You can access it straight up on Google. Just go on the internet, search it up. No need for software. It's all browser based, and you can even play around with it after this or something like that if you have spare time or if you're interested. But yeah, what it does is this one, it uses, once again, nearby gauged catchments that are hydraulically similar to predict regions without data. So it's kind of similar concept with before. And this one, it's the outputs that are slightly different. Well, quite a lot different. Whereas the previous one, you're looking at depth and duration. For this one, you do the same thing. So this is one of the attempts I've done, and this is just a screenshot. Catchment, and then latitude, longitude, and then and then you have the area of the catchment as well. Submit it all, and it should output something like this. Yep, you've got the date and time, everything's requested, all of that, and then you've got all this information. Here, 50% AEP for a 6-hour storm. This is the intensity you can expect, 7.7 millimeters per hour. If it's 2% AEP, so a more severe storm, even for 6 hours, you're still going to get like a lot worse of a storm where it's 17.56 millimeters per hour. Yep, I've got a few more things. Yep. Here, you've got the, this is more so, whereas the previous one, it gave you the depth with the AEP as well as the time. This one is looking at the AEP against the flow rates. 50%, 20%, 10%, 5%. And then I'm sure this is a bit of a throwback to, what was that course again? Was it 2002 or something like that? It's the statistics and numerics course. Well, you've got the lower confidence limit and then the upper confidence limit. So this course is informed a bit by that previous course with all the probability and the modeling and all of that. No need for MATLAB though, so that's a bit of a relief. And yeah, you still got statistics here, standard deviation, mean, skew, all of that. You can take a look at it in your spare time, but that's the kind of data you're looking at in order to, once again, model storms, right? Model floods, model storms, and then you can use that data and flood-proof your infrastructure, or at least try to have preventative measures or whatever, something down those lines. Anyways, moving on. Week 4. Week 4 is the last part that we'll be addressing here for this little session. Well, at least the first half of it. Akshara is going to continue in person after mine, and then I believe she's going to be talking a lot more into the groundwater side of things. So this is all kind of focusing surface level. This is all about, well, what's happening in the atmosphere. That's the first half of the course before week 6. What's happening in the atmosphere, what's happening in the surface water, your streams, your oceans, and then the later half of the term is going to switch it up. They're going to look at what's happening underground in the aquifers, in the groundwater, so on and so forth. That should be the same kind of course week progression as you will go through this year, but maybe it has changed since I did it last year. But regardless, okay, moving on. I keep getting sidetracked. Moving on. What is a catchment? The whole idea of it is it's a certain area of land that all drains to a certain point, right? And that's going to be defined by, well, the shape of the land, the terrain. Are there ridges? Are there divots? Are there gullies? You know, what about the trees? What about if you slap a metropolis or a city in the middle of that nice green field we have there? That's also going to affect the way the water drains, right? Concrete, you can't, your water doesn't drain through it unless you have like stormwater drains. So maybe if you have a big city in the middle, the water is going to flow around it or something like that. It gets a lot more complicated than that, right? But yeah, defined by the shape of the land, the terrain. Here's the key principle of it all, right? It's the idea that water always flows from a high point to a low point, and yeah, that is gravity, right? Gravity is going to make it do that. Flow from high points to low points. And there are 4 rules to delineating a catchment. Number 1, water flows in the direction of the terrain's steepest downhill slope. It's not going to flow uphill. Gravity is a thing. And path of least resistance. If it's going to be steep, it's going to flow down faster. It's the tendency. It's a tendency of water to follow the path of least resistance. And if the left slope of a peak is more steep than the right slope, the water is going to flow down the left slope because it's just easier. It's easier, path of least resistance, steeper, it aids with the flow. Streamlines are orthogonal to the elevation contour lines. So that's the idea is if you had contour lines drawn across a hill, across a gully, across the terrain, streamlines, so that's just the direction of the water flow, it's always going to be orthogonal or like perpendicular 90 degrees to the elevation contour lines. So actually I have a marker right here. Say for example, we had like, say for example, this is like the peak of the mountain, and then there's like a river or something. There's like a river flowing down here or something, and that's the peak of the mountain. Well, in a wet weather event where there's rainfall and then rain's falling on top of the peak, the water is going to be perpendicular. That is what we call the streamline. The streamline is going to be orthogonal to the elevation contour lines. That's what it is, yeah? And say, for example, this path that it's taking right now, I've drawn too many lines and now it's messy, but that path, say, for example, that is steepest, that's where the water goes. If, say, for example, this side, right, this side of the mountain is a lot steeper, maybe it's going into a valley or something, and then this one is just a plateau, well, then the water is then going to follow along that valley or whatever, because it is steeper. That is the rule of it, right? Okay, I feel like that got a bit too messy now. Let me just try erasing all of that. Not very good at drawing diagrams, but that'll do. Drainage divides now are found along the highest points of the terrain. What it's meaning is, actually, I think there might be a slide that explains it a lot better. There's like a whole diagram. I put it somewhere there. But yeah, we'll come back to this with a proper visual. And then streamlines do not flow towards drainage divides and do not intersect them. I'll talk about that later as well once I have the correct diagram. Let me just make a note here. Okay, yeah, we'll come back to that in a second later down the line. All right, moving a bit on here. There are 3 ways. Oh, actually, no. The next slide is what I wanted. Okay, well, just a bit out of order. That's my bad, but yeah. This is what I'm talking about before with the rules, the 3rd rule and the 4th rule. So this is one of the topographical maps I took from the lecture slides. And you see the black line here? That black line is what they mean by a drainage divide, right? That's the tallest part of the terrain. And maybe here it looks to be like a valley. It looks to be like a valley that goes down there. And what it means basically is at drainage divides, we were saying it before, drainage divides are found along the highest points of the terrain. That's what it means. On mountain peaks, on mountain ranges, or yeah, highest points of the terrain, you connect it all up. That's what you have a drainage divide. And what a drainage divide is, streamlines do not flow towards drainage divides and do not intersect them. It's the logic here. You have a peak, right? This is the highest point. This is, say, for example, we took a section, we cut this mountain range or valley in half, and you got something like this, right? You got the valley underneath, maybe there's a river there, but you got the 2 peaks, right? That's what the drainage divide is looking at. When you have rainwater that comes down here, it's going to go either this way or it's going to go either that way, right? Water will not cross back up over these lines. They will not cross back up over. It's either you go this way or you go that way. That's what it means to be a drainage divide. You either go left or the right. That's how it divides, and then that's how you collect water at the bottom of rivers and valleys and etc. But yeah, that's what it means by streamlines do not flow towards drainage divides and do not intersect them. You will not have water flowing uphill along a mountain. Gravity is a thing. And you also will not have any streamlines crossing over because, well, water just, you can't have it going like this, right? Gravity is going to pull it down. You cannot have water going up against a hill. Yeah, but that's the rules. That's the rules of catchments and delineating catchments. Okay, so that's what it really is all of these high points. you're looking at all the water in that area, within that red boundary. It's all going to drain towards a certain point of interest. And by the looks of it, you've got these small reticulation rivers, streams, and it goes through a branch, and it goes through like what seems to be like a bigger main river, and it all goes down to a point of interest. That's the outlets. Yeah. Do you see how it all it's like almost like the roots of a tree, right? Roots of a tree. It all kind of accumulates into one main part. And yeah, there's 3 ways to delineate catchments, 3 methods. One is a DEM, which is a digital elevation model. And what it essentially is, it's a 2D grid with elevations in each square, and you find the direction of water flow by looking at the steepest slopes. This doesn't work for depressions, and also the accuracy depends on the resolution of your DEM. So the more squares you have in your grid, the more accurate it's going to be. And even then, the examples or the questions that you'll do in exams and your assignments, it's an oversimplification of like what DEMs actually are, because you'll find out that there's computer models all dedicated to doing it automatically, and those models can get very complicated. Whereas whereas the one that you'll normally see in this course, it's a very like hands-on, by the book with a calculator kind of way of solving a DEM. So you can see here, you've got the grids, you've got the elevations and all of that, and that's what you're left with. And then you're going to have to solve it, right? These are like the steps you solve it with. And that's what I mean by it isn't the most accurate, right? It isn't the most accurate. You don't have, what do you call it? In these cases, you're only considering 8 directions of flow. You're considering down, right, up, left. Well, actually, it's not accurate to say down, up, right, left. It's more like north, south, east, west, right? And then you have like northeast, southeast, southwest, northwest. And that's like the only 8 directions you'll consider in these cases. Whereas in real life, that water can technically flow like at whatever angle it wants, right? It's water. It's going to flow where it wants to flow. So this model kind of only considers those 8 directions. It's a very rough one for high-level engineering. You're not looking in the details, right? You're just looking at the basic picture. So let me just erase it all so we can... How are we doing for time? We might give this a crack at solving. I'm not going to try solve the whole thing because it'll take a bit of time. But the idea is, say for example, 78, 72, that's going downhill, right? That's going downhill. So that's 6, right? 6 over 1. We're looking at slope. We're looking at gradient. That's a gradient or grade of 6. Going down this way, you've got a grade of 4 over 1. That's 4. Diagonally, you've got 78 minus 67, that's 11. And then 11, you have that over, that's where you bring in Pythagoras again, you bring in square root 2. Okay, and then you get a calculator out, you do the maths. From the looks of the answer sheet right there, it looks to be that the steepest slope is... Let me erase it. The steepest slope looks to be diagonal. Because you see here, it's going diagonal. That's where the water's going to flow. That's where the water's going to flow. So that's how you do it. You look at each square, you do the 8 directions, the 8 cardinal directions, north, south, east, west, and then the ones in between. And then you look at, well, what grade is the steepest? Whatever rainwater falls in that square, it's all going to drain towards the steeper gradients. Yeah? And say, for example, if this square, adjacent to it, there was an 84, well, there's no way it's draining upwards, right? It's not going to drain up the hill. The gradient 84 is a lot larger than 78. It's not going to go up. It's always going to go down. And then once you've done it for every single one of these squares, that's what I mean by it takes a lot of time. You're going to consider all 8 directions. You're going to end up with this network of arrows, and that's reflective of how water is going to drain in that catchment, or like in that terrain, yeah? And then you have flow accumulation, right? Flow accumulation, 0, 0, 0, 0. So all of these starting points, right? No water is draining into these squares. It's a 0. For this square, you've got 1 arrow draining into it, and then it accumulates, yeah? It accumulates until all the water collects at the bottom, and then you've got 24, right? This is a 5 by 5, 25 minus 1 for the 1 square it's on, 24. All the water is draining to this 1 square, and you've now identified like your outlets, yeah? And that's the gist of what a DEM model is. And then if you actually have proper software to do it, it gets a lot more detailed, it gets a lot more complicated. There's a lot more data points to work with than our humble 5 by 5 grid. All right? Yep, and that's what you do. You identify the outlets, and then you have these catchments by following the streams in reverse order, and then you have it. These are your catchments. Yep. Yep, different colors. I didn't even need to trace it, honestly, but that's how you would do catchment delineation. You do it step by step. The question will give you the DEM grid, elevations, then you figure out the flow network, you figure out the flow accumulation, and then you're looking at it, right? You're looking at it, and then you spot where the outlets are, and then you define the catchments. Simple as that. Now, the other 2 methods, I mentioned there was 3 ways to delineate catchments. Now you've got the Feesian method as well. I'm not too sure if I'm pronouncing it right. It's been a while since I've taken this course. But yeah, the Feesian method. What you do here is, it might be a bit more straightforward if I actually go back and forth between the slides. So first of all, you join each station to the nearby stations with straight lines. So yeah, stations, these are like weather stations. These are the stations where they measure rainfall, they measure meteorological data. That's where things are recorded, right? So a lot of times in a catchment, you're going to have multiple stations. You have station A, station B, station D, whatever. What it's asking for is join each station to nearby stations with straight lines. Done it here. Connect them all into... What you should be getting is a bunch of triangles, right? You should have triangles, triangles, triangles. If you have a polygon that has more sides than a triangle, you haven't created enough lines. It should just be a network of triangles, okay? That's a common mistake. When I first started, I wasn't sure well how to do this method. And then I had a square, and then you become very confused, right? But what you need to do is remember, every single polygon created should be a triangle. Then what you do is find the perpendicular bisector of each line. Every line that you've drawn, you go at the middle, you find every single middle point, as they've done with the blue lines here, you see? Middle point, middle point, midpoint, midpoint, midpoint. Find the midpoints of every single line here. And then what you do is you join them. You create polygons using the bisectors as boundaries. So you have the bisectors. Oh, it's a shame that I can't change the colors of my pen. But the idea is you have the midpoint, you extend it out. It's a perpendicular bisector. You extend them all out until they meet in, if you remember, the centroid of each triangle section. Once they meet in the center of each triangle section, you can then define these separate polygons using the bisectors. So forget about the triangular lines we've done. We're moving on now. We're using the bisectors, the perpendicular bisectors, and we're creating new polygons. As you can see, they even color-coded it for you down here. Now, after you get those polygons, you measure the area associated with each polygon, and a lot of times it's very rough. You're counting the squares of the grid. Maybe it's given to you even. But most of the times, you're just counting the squares and then estimating the area. And then you do an arithmetic average, right? You estimate the Fijian average rainfall, and then PTH, TH being Fijian, but then P is the average rainfall, and then however many n number of polygons, AI, area, PI, that's the do you see now how each station is then kind of in the middle of the polygons? That's the whole idea, is each station is kind of in the middle. If this catchment was a lot bigger and extends or something, and you have like other stations, all of these stations will be the centroids of their own polygonal region. Okay, and that's how you get the average rainfall. Is you're looking at, well, this is the amount of area dominated or dictated by each station, and that station recorded an average rainfall of that. You're doing a weighted average. Okay, and with that number, whatever number you get, that is the average rainfall for that whole catchment, that whole area. That's the average rainfall. Now, lucky last, we've got the isohedral method, and very similar. These are all just ways of estimating the average rainfall for a catchment. Isohedral, what you do is you draw lines of equal rainfall. These lines are called isohets, and then they're very similar to a contour map. You know how contours, you're going to be doing, you're connecting the dots between each area, not each area, each point that has the same elevation. You're doing the same, but you're drawing lines of equal rainfall. So point A here and point B here, they have same rainfall of 5 millimeters. I'm going to draw a line and I'm going to linearly interpolate between whatever measurements I have. And they've done it here. It looks like a contour map, but you're using rainfall instead of height or elevation. Then you do something very similar to what we did before with the Fijian method. You're going to go in and just hand count every single square. It's tedious, but that's how they do it. You're just doing a rough estimate of the area. What is the area? And then, yeah, you just look at the area enclosed by two adjacent isohets. One here, and then the adjacent one being here. You're looking at, well, what's the area in between all of that? And then you do it for every single section until you've covered the whole catchment. Okay, you're doing it for every section as well, all the sections. And then you use this formula here. Oops, I've kind of covered it now. And yeah, you use this section here, or this formula here, pj minus 1 plus pj over 2. So that's just taking the average of this isohet and this isohet's rainfall. This one, it's labeled as, let's say 5, right? Let's say 5, and this one's 8.8. Oh, excuse my bad handwriting. 8.8 and 5. You're taking an average of both of them. That's like around 6 point something. I don't have a calculator. That's probably what it is, like 6 point something. That is the average rainfall, okay? And then you're doing the same thing where you have the arithmetic mean. Same idea. You're just taking the weighted average of all the rainfalls in this area, and then you can figure out what's the average rainfall. And those are the 3 methods. Now, that's basically all I have for you for this session. Going back to the beginning, yep, so we just covered evaporation, evapotranspiration very quickly, covered rainfall a bit, stream flow, we skipped. Same with radiation. They didn't mention it here for some reason, but radiation's a part of it. Flood frequency analysis, very lightly touched on it. We're not touching on FLAC at all. Week 3, design rainfall, regional flood frequency estimation, catchment delineation, losses and rainfall runoff modeling. Good luck with that. Good luck with that with your lectures. And yeah, if you're watching this in person now, I'll be handing it off to Akshara. Hopefully you've learnt something. Hopefully it's been helpful. But yeah, I mean, yeah, enjoy the rest of your evening.
Okay.
Bye.
Bye, Janice. Thank you so much. Okay, wonderful. Whoops. Let me open this up. Okay, so that was hydrology. That is probably about, I'd say 70% of the course. The other 30% is groundwater resources. So that is everything about how water moves and behaves underneath the ground and how we're able to kind of like track that and I guess predict it as well. So with the groundwater course content, there are 3 topics. The one that I'm going to cover is the first one, so it's the groundwater resources and flow equations topic. That's probably, it's the most important for this entire section of the course just because it'll contain all of the fundamentals, the physical properties of water, water potential and hydraulic head, groundwater movement and transport, and also steady state flow. And those are all really important concepts to know when it comes to groundwater resource engineering. So I'm going to cover all of those today. The other 2 topics are to do with aquifer properties and borehole construction. So that will be a lot to do with the properties of an aquifer, which I'll explain what that is in a second, and then borehole construction. So boreholes are used to access groundwater, which sits in the aquifer underneath the ground. Then topic 3 is the pumping test analysis and the occurrence of groundwater. So you will look at the modeling of groundwater flow into a well. You'll also look at the analytical solution for the radial flow equation and how geography impacts the movement and dynamics of groundwater. So like Janice said, there are some really good class notes in this course. So for those 2 topics, topic 2 and topic 3, I would recommend looking at those, but I'm going to move on to, I guess, the groundwater fundamentals now. So I think this is a really important part of the course to learn well, just because for a lot of you, I guess the most recent water course you've done is fluid mechanics, where you don't necessarily get to learn that much about how that theory is applied. So I'm going to go through it kind of slowly, but if you have any questions, please let me know. So why is the study of groundwater important? Basically, in water engineering, you will need to look at groundwater dynamics for water supply, dewatering, and contamination remediation. So that's when if you're about to, for example, start a project and the site has soil that is contaminated, you have to know how to either remove that contaminant or manage it, which you won't be able to do without knowing the fundamentals of groundwater and how it moves. The notes in this course are SI quantities. With water courses in general, it can be really difficult to keep track of your units. So what I would do is just get really comfortable with converting them as you're solving questions. And yeah, in the groundwater notes, there's a really nice unit table, which I would recommend looking at and not memorizing, but definitely keeping track of. Okay, so I'm going to start with this diagram here. This is, I guess, kind of a profile view of what an aquifer could look like, a very basic one. So if we look at the ground here, there's a lake there, and then underneath that there's the water table. So in fluids, you would have learned about what the water table is. That's just where the water level sits, I guess, most of the time. And that's sitting on top of the unjoined limestone and shale. And those 2 levels create what is the sandstone confined aquifer. So that's where the water is contained underneath the ground, right? So a couple of really important definitions from that diagram, terms that will definitely be thrown around across the whole part of the course. Aquifer, that is a permeable geological unit. and it can transmit really high water volumes. So if you look at this part of the diagram here, the aquifer, it's got quite a lot of water that can transmit water from one place to another, not necessarily connected to the water table, right? The aqualude is a saturated geological unit that does not transmit any water volumes under gradients. So there's already as much water as there can be within that aquifer, so it won't be transmitting anything, right? The only reason why water is able to move is because there's an open pore space for it to actually go. So if it's fully saturated, then it's not going anywhere, right? The aquitard is another geological unit. It can transmit water volumes, but not enough to allow the completion of well production, which I won't go into that much detail in this crash course, but you definitely will hear about it in the course content, so keep an ear out for that. Now, an unconfined versus a confined aquifer, what does that mean? So unconfined is basically it's open to the atmosphere, and then a confined aquifer means it occurs between two aquifers, right? So kind of like this one here. So the shale and the unjointed limestone, those are two aquifers that I guess compress, or they like contain the sandstone where the water is able to be stored. And then lastly is the piezometric surface. So a piezometer, as I'm sure you've heard from fluids, is just a way to measure the height of water that rises to determine things like water head, for example, or water potential. And I'll get into that in a second, but I will just cover very briefly the physical properties of water. And I really wanted to do this because I'm sure it's kind of been a while since you guys did fluids, or if it hasn't, I'm not sure how much you remember. So none of what I say in the next few pages will make sense if we don't go through this first. So viscosity, very quickly, is just the resistance to movement of one fluid over another, which is like an adjacent fluid. This is the symbol here. I do know what it's called, but I'm forgetting it right now. It's tau, thank you very much. So that is your shear stress. Your dynamic viscosity down here, that's what you're measuring. Like I said, the resistance to movement of one fluid over another. And then it is multiplied by changes in velocity, right? And the units for that are centipoise, which I also learned was a thing recently, and it's just the thinness of a fluid. Which makes sense if you think about it, because viscosity, like thick fluids, won't move as seamlessly over another fluid, I guess. Fluid pressure is the force per unit area which acts on any reference point or chosen point in a standing body of water. So in this equation here, P is the fluid pressure. This symbol here, that's the height of the water column above the reference plane. And then you've got density and gravity. Again, remember your units for pressure, that's in pascals or kilograms per meter per second squared. If conditions are hydrostatic, the pressure, or the P, is equal to the column weight above the cross-sectional area of the reference point. So that's just like a fun fact for you to remember. Hydrostatic might just be thrown into a question, and so this is just a fun thing for you to remember, and it'll help you out with the equations and everything. Gauge pressure is pressure registered by the gauge with the atmospheric pressure as a reference. So it's just any additional pressure that's not, I guess, provided by the water that's connected to the atmosphere itself. Compressibility is reflective of the stress and strain properties, and it's just a measure of linear or volumetric distortion. So the change in volume of a fluid parcel as it moves through the volume at a control volume, for example, which I will get more into later. Stress as well is the internal response to the external pressure, which is imparted through the hydrostatic pressure here, right, or the fluid pressure, right? So all of those terms are kind of interconnected, so it's really useful to know what they all mean just for when you're doing your questions. Okay, and then we'll move up to this section here. Another property of water is porosity. So under the ground, water is stored in those aquifers, right? And it's stored inside the pore space of unconsolidated material and rocks. But there are two kinds of porosity, right? One is your primary porosity, which is, I guess, your default porosity. It will always be there, and its degree will depend very heavily on the properties of the solid and rock material. And then the secondary porosity, that will need to be considered if there is a secondary solution. So that will become really important, for example, if you're dealing with a contaminated site, because there's probably another solution in there aside from water, so it's not really a simple primary porosity problem. And it could also be due to fractures of the rock matrix, which will obviously have a very big impact because the water will find extra space to, I guess, travel through. Okay, a really, really important part of this course, water potential and hydraulic head. So I'm going to go through this part kind of slowly. Basically, this formula here is what we're going to focus on, and then you'll see that throughout the terms that I've just basically gone through, you'll see how they impact the overall water potential, right? So what is water potential? The water flows in response to changes or slopes or gradients in water potential. So it is the potential per unit mass of water in a system. It's measured in joules per kilogram, and there are different types of potential or different components that contribute to the overall total water potential, right? So firstly, there's the metric potential. You don't really need to know what that is in a great deal of detail. Often it will be just cancelled out. I'm sure there's more information on it in the actual lecture notes, but for this purpose of this crash course, I'm just going to skip over it. Velocity potential is up here, so that's this section there. That basically comes from the energy per mass which is provided by motion. So if water is moving, then energy is, I guess, added to it, right? So V there is the velocity of the actual groundwater, which is usually less than the potential provided by gravity, right? Because groundwater moves really, really slowly because it can only move through open pore space. The next one, speaking of potential due to gravity, that's just the product of acceleration forces due to gravity multiplied by z, which is the distance from the point of measurement to the reference level where that total potential is equal to 0. So wherever your reference level is, and I'll show you a diagram where that will be indicated in a second, but whenever that is 0, that is your reference point. So that's gravity potential. And then pressure potential is down here, and that's this equation here, which is just your fluid pressure divided by the density of water, or it's the gravity multiplied by the depth of the water column above the reference point. And when you add all of those little components together, because water can, the potential of water can be impacted by many things, you get the total water potential, and that will tell you how much head there is and if there are any changes in energy across the water body. Okay? Does anyone have any questions about that formula or how any of the components link to it? No? Okay, perfect. All right, so that's a huge formula, or it's not huge, but there are many components to it and a lot of terms that we don't really get, but a lot of the time that can be simplified, right? So we're about to simplify it right now. For flow prediction, which is super important for groundwater, in fully saturated aquifers, the total water potential just reduces to the pressure and the gravitational potentials, right? So remember how I said earlier that if an aquifer was completely saturated, the water wouldn't be able to really move anywhere because there's no open pore space for it to travel. This is basically me like reiterating that. So the velocity potential that I talked about here won't be a factor that contributes any energy to the overall water potential because it is a fully saturated aquifer, right? So it's only the potential from pressure and gravity that comes into play there, right? And if the density is constant, which it usually is if it's water, then the hydraulic head, which is just the little h there, that's how it will be notated across the whole course, is equal to just the pressure head plus the elevation head. So that's just that there, right? And it can be reduced to this equation, right? So that's a lot simpler than this big one here. Does anyone have any questions about how this big formula can be manipulated based on the condition of an aquifer? Okay, wonderful. Okay, this is just a really useful diagram. I find it good because you can kind of see, basically you can apply all of those symbols and everything to an actual diagram, which will often be in the question or in an exam or whatever. So there are your symbols here. As you can see, water potential, water pressure, and hydraulic head. So it's important just to note the parts that I've highlighted in blue. So those are really important because you get to see the relationship between each component. So you can see here, for example, that the, I guess, what's that one? The pressure head is equal to that elevation there, and then the hydraulic head here. So that will give you the total pressure head, which is why this is called the piezometric surface, because that's where you can, I guess, you implement or you install the piezometer to measure the pressure overall, and those are the measurements or the values that you need to figure out in order to actually get that value. And yeah, this is the same thing over here. And that's kind of it for that diagram, I guess. Does anyone have any questions on that? Okay, great. Okay, so that was the, I guess, very, very brief overview of the physical properties of water. Now we're actually going to go into groundwater movement and groundwater transport. So basically applying those terms to basically figure out how groundwater is moving underneath us and how we can track its transport as well. So a lot of the groundwater movement can be tracked, like I said, using a piezometer, because using the piezometer you'll be able to figure out any changes in hydraulic head or water potential or whatever. So the piezometer will be able to determine the elevation of water, and it will do that by taking a measurement at the piezometer base, right? There are a couple of terms that we should probably go through before we get into how it's measured. So in terms of how you calculate it, there are lines drawn connecting 2 points of equal hydraulic head. So that's when there's been absolutely no change in velocity, density, pressure. The water potential is completely the same at these 2 points. And so they have equal hydraulic head, right? And so those lines are drawn connecting those 2 points, and that's going to be a horizontal line. And that horizontal line is an equipotential line, okay? Like I said here, I guess those cross sections are really important when used in groundwater resources and are known as piezometric maps or potentiometric maps. Okay, so often for groundwater flux, flux is just like the flow of material through from one point to another, and it's I guess a volumetric rate, I guess. So vertical components when measuring groundwater flux are often neglected, and the horizontal components, those can be used to determine and I guess construct those really important equipotential lines. Okay, so with the gradient of hydraulic head, like I mentioned earlier, water moves in response to changes in the hydraulic conditions, right? So the hydraulic gradient is equal to any change in hydraulic head divided by the distance between those points, right? So basically the average amount of change at each point from A to B, right? The piezometers, they're used to determine horizontal and vertical movement of groundwater, and the gradient of the hydraulic head is just like this equation here. Here's a diagram to kind of show you how that works. So here the hydraulic head from this point to this point is just 20, and then you divide it by the distance to get the ratio that you're looking for, the gradient, this one, 0.10. Does that make sense to everyone? Or would you like me to go through?
Is that like the same, like that row of diagrams are like related to the same like scenario?
The one
like
from above here? This one?
No, like what you just explained.
Oh, over here?
The diagrams themselves. Like
they're just diagrams to show how, I guess, elevation and hydraulic head and distance are related. So they're not specific to any, like I wasn't explaining any specific situation here. And then the equipotentials were just to show you like the line, or to define the line that's drawn between two areas of equal hydraulic head. So technically for this part here, you're looking at changes in hydraulic head. So that wouldn't be relevant to this because the hydraulic head is equal at an equipotential line. Does that make sense? I don't know if I explained that too well. Okay. Oh no, I'm missing the word equations here. Let me just really quickly add that in. Okay. Now we're going to go through flow nets. So if you've done soil mechanics, actually, you'll know what a flow net is. But if you haven't, that's okay. They're not too bad. So it's just it's a two-dimensional diagram that just shows the flow of groundwater on an XY plane, right? Or an XZ plane if it's if you're looking at vertical flow or change. And the reason why it's so important in soil mechanics is because it allows you to see obviously how the water's flowing and where it is at a certain given point in time or under a certain amount of pressure, right? So the reason why we're going through this now is because basically we just learned about equipotentials, right? So equipotentials will be able to define any changes in head. So, and it'll be distributed over those 2 points, right? And then the flow lines, which are drawn as like right angles to those equipotentials, are used to create your flow net, which is an example here. The flow lines will tell you as well the direction of the flow. So you'll see like there are arrowheads showing what direction the flow is going and everything. And you can kind of see like where the flow is like collecting here. That's kind of where the water table will end up being as well, or it'll like collect there. Anyone have any questions about flow nets? I can't go through them in too much detail, and I don't think you'll go through them that much in groundwater, but they are important to know just in case you get a question where you have to like interpret it or something. Okay, so now we're going to go through the measurement of head at a flowing well. So a flowing well, or otherwise known as an artesian well, which I also just learned recently, basically it brings groundwater to the surface without the need for a pump, because the water is, or the pump is, the well is under pressure within the aquifer. So if you remember the hydraulic head equation, little h is the hydraulic head at the flowing well. This one here, that's the density of water. This is the gauge pressure. So within a well, it actually won't be, it'll be gauge pressure because it's not connected to the atmosphere. And so the only amount of pressure, like actually impacting it, will be the pressure from the gauge, I guess. And then Z is just the distance to the reference point, the vertical distance. Okay. In terms of what the factors are that are impacting the hydraulic head, there are a couple of things. One is groundwater recharge. So that's water moving into the ground through like rainfall. And if groundwater recharge occurs, the way that that impacts hydraulic head is that the water table is replenished, right? Evapotranspiration, which you would have just heard Janice talk about, is the process by which water is evaporated from soil and transpired from plants. So it's the combined process of both of those functions. And then other things are just tidal effects near the ocean and earth tide effects. Okay. All right. Going okay for time. These are some other factors here. I won't really go through all of them, but there are quite a few environmental occurrences that will impact groundwater. So agricultural irrigation, deep well injection, earthquakes, geotechnical drainage, all of which will have an impact on the way water moves under the ground. Okay, so now that we know a little bit about the values that we need to know to understand groundwater movement, we can look at groundwater transport. So the actual transportation of a fixed or controlled volume of fluid from point A to point B, right? So what is really, really important for your groundwater course is the Darcy's experiment, which will be really important for your assignment actually. So what the Darcy's experiment is a way to, I guess, get quantitative data on how water flows through a porous medium. So it's just a circular cylinder where the cross section is notated as A, and that is filled with sand or like glass beads or whatever is in the lab, and it's stoppered at both ends, right? Those ends are then fitted with an inflow and outflow manometer and tube, and then water is, I guess, allowed to flow through until the pore space is entirely filled, right? So until the volume and the speed of the volume like going into the cylinder is equal to the volume coming out. The datum is at z is equal to 0. These are the notations here, which you'll see, I guess, in a drawing of it. I don't have a diagram of the Darcy's experiment, but there is definitely one in your lecture notes somewhere. I just have to find it. I might go back and insert it into these notes after. But the important part about the Darcy's experiment is that's how we get, or how we're able to visualize Darcy's equation, which shows us a really, really important relationship between a bunch of different components. So the first is the water velocity. The second is hydraulic conductivity, which is notated by the capital K. And that is a measure of how easily water escapes from a porous medium. And then all of that is multiplied by any changes in hydraulic head all over the horizontal distance. right? And there are two ways for you to, I guess, write it. They're both the same. This is just rearranging this equation here and making Q the subject. Okay, so those are two really important equations. Okay, so now we're going to look at intrinsic permeability, and the reason why we're looking at that immediately after Darcy's law is because it's just a little bit more of a focus on this new term, hydraulic conductivity, which we don't really know that much about yet, right? So remember, hydraulic conductivity is a measure of how easily water is able to escape from a porous medium. And so obviously, K, or hydraulic conductivity, is a function of that porous medium and is a function of its porosity and the degree of interconnectivity. Okay? Viscosity and fluid density are also important values, because if you remember earlier in the crash course, I said, for example, that viscosity was, I guess, measured in that centropoise unit, which is the thinness of a fluid, and that makes it really easy for, if it has a high degree of viscosity, it makes it really easy for the water to flow through the cylinder, right? So that makes it super easy for the water to escape that porous medium. So the following relationships relate all of those properties to V. Okay, so this one's here. So we can rewrite V to equal these equations here. There is information on the derivation of these, but again, they are in the lecture notes, and because of time, I don't want to go through them just in this crash course. But basically, the important parts that you need to know are D here, the little d. Those are the diameters of the particles within the porous medium, which will have a huge impact on the degree of porosity inside the cylinder. And then capital C is the dimensionless constant of proportionality, right? And since proportionality and the little d are both properties of the medium, which is the, I guess, sand or the geotechnical material in the aquifer, for example, like the limestone or the sandstone in this diagram way up here. Because C and D are both components related to that, you can kind of simplify them into one constant, and that is equal to little k. And that is the intrinsic permeability. That's the constant that we're kind of talking about here, right? And because k can be simplified to this, this can be simplified to k, you can sub k into this equation up here to get a really simple equation that will tell you the hydraulic conductivity, just in case they don't give you hydraulic conductivity as a constant in your question, right? Does anyone have any questions about Darcy's law or how Darcy's law can be simplified or the properties related to Darcy's law? Okay. All right. The last kind of topic related to groundwater transport is the difference between specific discharge and linear velocity, or average linear velocity. So the reason why I'm covering this is because it's really a common mistake for students to mistake specific discharge with average linear velocity, because they're both, like velocity, right? And they're both like denoted with V sometimes, but that's not correct. So V, little v, will almost always be your specific discharge, okay? Specific discharge represents the hypothetical speed at which water will flow through the aquifer, or in Darcy's experiment, the cylinder, if it was an open space. So if there was no if there was no material in there, if there was no sand or anything, and it was just a completely open conduit, the speed at which the water flows through that conduit would be your specific discharge. Does that make sense to everyone? Whereas the average linear velocity is the speed at which the water is flowing through the porous medium, right? And this is a little bit hard to explain, but if you just visualize the porous medium and you visualize the water flowing through only the open space, right? If you take all of that open space and you collate it, I guess, ignore the sand and everything, if you calculate the amount of space that is left for water to flow through, then that area is going to be smaller than the open conduit, right? Does that make sense? Okay, let me draw it. So here we have an open conduit, right? And water is just flowing through it, right? This is your specific discharge. Does that make sense? Okay. The average linear velocity is the speed at which the water is flowing through a porous medium, right? So obviously the amount of open space in this conduit is not equal to the open space in this conduit, right? So water's flowing through both of them, but it just has less open space to use, essentially, right? And so the amount of, I guess, open area in this conduit, this one here, the open one, is going to be a lot more, the circle is going to be a lot wider than the amount of open space in this conduit. And so the reason why that's really important to know is because the average linear velocity is going to almost always be, where's the notes on this? Oh yeah, okay. The average linear velocity, because it's talking about this conduit here, is almost always going to be faster than the one flowing through the open conduit because the area is smaller, right? And that's the laws of fluids, if you remember from when you did 2500. Does that make sense to everyone? I know that was a bit of a rabbit hole to go down. But essentially, there is a formula for average linear velocity, and that is the volumetric flow, because we know that that's a really important, that's the value that I guess determines how quickly these water volumes are flowing through the cylinders. And then you've got the effective porosity times the area, right? And the effective porosity is usually less than the total porosity because some fluid remains trapped in dead end pore space. So the water can't actually flow through, so it's just left there, adhering to the grain surfaces or the bead surfaces or whatever's inside the Darcy's cylinder. Anyone have any questions on that? Okay. All right. We are making okay time. And we're nearing the final section of the groundwater crash course. So now we're going to go through groundwater flow equations. Now, in this section of the course, there are many formulas, and there's a lot of information about the derivations of each. I'm just going to go through the important ones that will teach you at least all of the notation that you'll need to know to at least understand those formulas, right? But what I would recommend is that as you're revising or whatever, when you get to this part in the course, because you might not remember everything that I've told you today, is just keep a record of each of the notations that I go through so that when you see them in week 8, I think, you'll at least have a vague idea, okay? So, where do we start? So, groundwater flow equations. The the model that describes water flow in a saturated medium is provided by Darcy's law, right? If hydraulic head can be measured, the direction and also the rate of movement can be predicted if we have hydraulic conductivity. Okay, that's important to know about Darcy's law. Now we need to figure out a model for groundwater flow, because it won't always be completely saturated, right? So the law that is really important in groundwater flow equations is the conservation of fluid mass. So that's the mass of the inflow minus the mass of the outflow. So that would be the mass change, or the amount of stored mass change with time. So this diagram here, this is going to be kind of our reference for this part of the crash course. It's like your control volume. That's a term that you would have learned in, I think, a few other courses, probably soils and fluids as well. But when it's chosen, the volume should be larger than the representative volume. So the average velocity should hold as an accurate representation of the fluid, right? Sometimes it's abbreviated to REV, so if you see that in your lecture notes, that's basically what they're referring to, just the hypothetical control volume and the volume of fluid within this cube here. So all of the space in there that's filled. Does that make sense? Okay. And basically what we're about to figure out are the fundamental terms required to figure out how much and how quickly the fluid is flowing through this specific space, right? Because that will then give, I guess, a groundwater engineer information of how quickly the groundwater is flowing through an enormous aquifer, for example. It's just scaling it down a whole lot. Okay, so the thing about groundwater is that there's a lot of conditions that you have to figure out. So the law of conservation of mass for steady state flow conditions through a saturated porous medium, right? So in this case, it's steady state flow and it's a saturated porous medium. For those conditions, the fluid mass flux into the elementary control volume, which is the diagram in figure 1.9, is equal to the fluid mass flux going out of that control volume. So there is no change in the mass quantities stored in that volume. Is that something that we're all comfortable with, that concept? Okay. So in figure 1.9, assuming that it is, again, steady state flow and a saturated porous medium, the mass inflow through ABCD, so this phase here, is equal to JX. So we're also only considering the horizontal direction in this case. And that's equal to the JX coming out of EFGH, that face there, right? But that might not always be the case. Like I said, it might not always be saturated and it won't always be steady state flow. So we need, I guess, part of the equation to account for that, and that's this here, right? So that's any change in mass flux in the X direction. Have we got that so far? Okay. If you apply that to all directions, you get these three terms here. And when you add them up, you get the total net mass outflow, okay? Now, when that total net mass outflow sums to 0, again, we have steady state because there's no change in mass. I guess it's important to note that in groundwater systems, almost always they will be in steady state flow, but over a very, very long period of time, right? But more often than not, because groundwater moves so slowly, it won't sum to 0. and there has been a change in quantity of mass that has been stored in the aquifer. So that's non-steady state flow, and that's the condition that we're dealing with for most groundwater systems. Okay? So if we just look at the steady state flow equation, the only difference is that there's a zero here, right? But just to, I guess, simplify things, if J is equal to the mass flux, which is the volume flux times the density, and all of these terms will give you, I guess, the change or the flow of volume flowing in and out of this diagram there, then you can simplify this formula, this one, right? Because no one knows how to deal with that. So the first thing that we do is that we take out fluid density, right? Because more often than not, that is not going to change, okay? So we've taken it out, or we've factorized it there, and we've left everything else. Next, we also know that the fluid density is not going to equal zero, right? So what we know now is that this component does. We also know that the velocity components can be further simplified using Darcy's law, which we learned about up here, right? That one there. Okay? And when we apply those two formulas, our overall steady state equation becomes this here, right? It's getting longer, I know, but I promise it will get shorter in a second, okay? You'll also notice that now the expression is positive because K, capital K, which is our hydraulic conductivity, is a negative expression. Another thing that we know is that if a medium, like the material of your aquifer, is isotropic, which means it's got the same physical properties, like throughout the entire volume, we know that the hydraulic conductivity for that medium is going to be exactly the same in all directions, okay? And we know that because there is a medium there, it's not going to equal zero. So again, we can take it out, we can factorize it. And that gives us this equation here, which, if you remember Math 2018, I want to say, is Laplace's equation, right? So Laplace's equation is really important when it comes to groundwater because you're essentially simplifying all of these components here because you're factorizing all of the constants and getting rid of all of the common terms. Does everyone understand everything that is in bold here? Yeah? Any questions at all? Okay. All right. Now finally, the last two terms that I wanted to talk about. Obviously, when you do your groundwater equations, you're not going to have to apply Laplace every time because it's iterative. And so what you want is to be able to simplify that and use an approximation, right? And that is where my crash course ends, but again, I've told you all of the terms that you'll need to know to understand the replacement of Laplace's equation into the actual equations that you'll need to solve groundwater problems. The only other terms that you need to know are T and R. So, like I said, there's a section on how the partial differential equations are replaced. And the new equations will include R and T. So R is just your rainfall discharge or recharge constant. So that will allow you to account for any water table replenishment, or I don't know, if you're in a drought, then it'll allow you to figure out how quickly the water, drained from that water table. And then T is a product of hydraulic conductivity and the aquifer thickness, which is little b there. And essentially, after all of the derivations, you end up taking this, which is our original steady state flow equation, just with the R added onto it. that will be your three-dimensional representation of steady-state flow. And this will be your 2D representation of steady-state flow because you're taking into account, I guess, like a vertical, not vertical, the thickness value, which is just like in a cross-section, it'll be that there, your aquifer thickness. Whew, okay, that is all for the groundwater crash course. I will share all of these notes. I will add the diagrams that I said I was going to add, but does anyone have any questions at all about what I've covered? Okay, then I will wrap it up there. Thank you so much for coming and all for watching. That's the end. Wait. Let me end it.
Oh, try the second time.
Oh, what is happening? Oh god, I'm gonna have to edit this, aren't I?
You need to stop watching the stream.
Oh yeah, you're so right. Okay, let me cross that.
Oh, yeah.